Hello, my name is David Cartwright, and I am going to be taking you today through the growth models of COVID-19 instances. All right, let's begin. All right, we're going to understand the growth of these of COVID-19 through hands-on explorations. And we're going to find out through all of our studies that it's an exponential kind of a growth. You've been hearing that word, I'm sure, throughout this whole virus kind of thing. And we're going to take it to the next level, actually, because we're going to define what an exponential function is. And we're going to be able to tell the difference between linear and exponential growth. And we're going to do that through graphs. And we're going to do a whole lot of hands-on activities, well, some hands-on activities to get you in the mindset of what exponential growth actually is. All righty. The reason why we're going through all of this stuff is because in the real world, in the world that you have, we have a new thing that's out. And this thing is the coronavirus. It's a respiratory, it's a breathing virus. It affects your lungs and all of that kind of thing. It affects more than that, but the deadly part about it is it really does affect your lungs. We really don't understand this virus. We have more understanding of the flu than we have of this particular virus. We have medicines and vaccines for the flu. And when flu season starts, these things are administered to prevent sickness and death, but we do not have a vaccine for this novel or new coronavirus that we have. And since we don't have natural defenses against it, it is making a whole lot of people sick and it is killing a whole lot of people. All right. So we try to, what is it? To try to lessen the disease as far as its spread is concerned, because it is very much alarming how this thing is growing. So to do that, we do social distancing. Some people call it social distancing, but it's actually physical distancing. Excuse me, take a drink. Thank you. We need to wash our hands. We need to use that alcohol-based sanitizer, and we need to practice really not touching our face. And we really need to wear masks everywhere we go. If you're not with immediate family and all that kind of stuff, if you're traveling outside, then you really, really need to wear a mask. These are the things that we're doing to stop the spread of the coronavirus, which brings up some questions. United States abruptly shut down, just like every other nation. And it remains closed in part to this day. So the questions could come is, why did we have to shut off everything so abruptly? Why couldn't you go back to school? Why didn't we have regular graduations? Why can't you go visit grandma? And why can't we hug our loved ones and family members who are in nursing homes or in hospitals? And the answer to all of these is that the coronavirus is very much worse than anything that we've dealt with thus far. It's certainly it's worse than the flu. The death rate of the coronavirus up to now is in some places it's 9.5, some places it's 44 times as much as people with seasonal flu. In other words, you are much more likely to die if you get the coronavirus. And it's really not like the flu at all. It's really much, much worse. Let me see. So the death rate is worse and it is more contagious. It's more contagious than regular flu. If you have the flu, you're probably contagious about, you're contagious about, you'll be contagious for about 3 days. A person with COVID-19 is contagious for twice as long, 5 to 6 days. That means you have more of a chance to spread it. The youth they carry the virus and they seem asymptomatic, which means that they don't show any signs of the disease, which means that you could be running around and you could actually have the virus itself living inside you. And you could be spreading it, shedding virus everywhere. That's why you have to wear masks so that you do not contaminate other people that are around you. Masks are not necessarily for you per se, but they're for everyone around you. And so, and here's the thing: the youth, they don't die. It's not as serious. There are some serious COVID-19 infections in young people, but it's a low rate that these serious infections happen in young folks. But it is very high for the elderly and those having underlying health conditions, diabetes, and all of that kind of thing. And you just never know who you're going to run into. So masks are very much important in this pandemic world. Let me see. So if nothing were done, if we didn't do these measures like closing schools and all of those kind of things, we would overwhelm our health systems. There are some states now, this is July the 3rd, 2000. And at this date, Florida and California, they're thinking about and have in some counties, they've closed things because in Arizona too, because their health systems are being overwhelmed. They don't have enough beds to house the people that are getting sick. If we didn't do anything like at the beginning of March, then there would be no personal protective equipment, or not enough for medical workers. And unfortunately, if we didn't do anything at all, there'd be a whole lot of deceased people, whole lot of deceased people. And you would have to start thinking about where you would house those bodies so that you could do other things. The management of those dead bodies would be crazy. So we had to do something. We had to do something. So the question is, can we use math to model the growth of the explosive growth of COVID-19? And we can. We can. If we look at this graph here, the solid line indicates the actual growth of this pandemic for the first 80 days inside the United States. This dotted line is the linear model of that particular, of this particular data. It's a linear model of that particular data. According to this R squared number, this number says that 50% of the actual data is actually being modeled by the yes. White came in. Is linear data is being modeled by this actual data. 50% is not good. So we have this exponential model here, and it models about 92% of this particular data. And we can fine tune this equation, this exponential equation right here, to even get a closer representation for this line right here. So this line, this darkened line here is indeed an exponential model, and so now we want to, since now we know that the actual growth rate of the virus kind of mimics or greatly mimics this exponential model, we want to learn about exponential growth and to find out how that happens. All right, here we go. So the first thing I want you to do, students, is to get a piece of newspaper. You got to get a piece of newspaper. So have somebody give you a piece of newspaper, or you go around and get one. If you don't have a piece of newspaper, just get a piece of regular paper. Newspaper works really, really good for this though. And I need you to go to this website, students.desmulse.com, and I want you to type in this particular code. That code brings you into a particular demonstration that I have already set up for you. And so I need you to leave, I need you to go to this particular website, type in this, And with your piece of paper, you're going to go through a set of instructions. Um, you're going to go through a set of instructions and a whole hands-on kind of a thing. So I want you to go ahead and do that now. We are going to sign out for a moment, and we will see you on the other side of this. All right, go now. All right, I'm back. All right, so we are going to watch a couple of videos and we're going to see whether we can do this well or not. Hold on, I'm going to do my computer. I'm going to do this for a moment. Then I'm going to do this. And then I'm going to do this. Yes. All right, I think I have what I need to do. Okay, so the video one that we're going to do, we're going to look at this video, how folding paper can get you to the moon. And we want you to think about, again, exponential growth. You just went through a hands-on experience with paper folding and all that kind of thing, and we learned about exponential functions. Let's look at this video and see what we can see. All righty. Hamilton is something you should probably see if you haven't done it yet. I'm going to skip that. righty. That was that TED Talk. That is that particular thing. Let me see if I can get out of this. Okay. All right. So the paper folding experiment is what it is. And so it's kind of amazing that you can make 48, I mean 46, 40, 46 folds and get the distance from the moon and back. Now, you're kind of asking this question, why in the world am I talking about paper folding? Why did I take you through these exercises? What I'm trying to get you to understand is the link between how exponential growth is on a sheet of paper and to the link of how exponential growth grows in a virus. So if if we say that we start with two folds of paper, it's like starting with two people that are infected with the virus. So first you start with small numbers, but if you continue to double it, 4, 8, 16, 36, 64, and on the 16th day of this doubling process, you'll have 65,536 people that are infected. On the 20th day, you'll have over 1 million people infected. And if just 20% of those, if we multiply this number by zero point 0.2, if we just have 20% of these people, just 20% of the people that are affected, if they were hospitalized, then you have 209,715 people, a big number of people that are going to hospitals. There are not a whole lot of intensive care units, and they don't have a whole lot of beds. And so you can see where this many people could could very much overwhelm a medical system. That's what we're trying to prevent. All righty. Now, we want to go ahead and do another video. This is from the movie Contagion. This is very eerie. This movie was made 2011, I do believe. It's kind of eerie. If you have never seen this, hold on to your hats. Here we go. See if we can do this. All right, here we go. Sorry about that, folks. I'm getting better. So the message of that is kind of eerie because it talked about how it spreads. It talks about they had no vaccine. You saw emptiness everywhere. Yeah, it's kind of like where we are now. So that's what they were trying to prevent with social distancing and all of those kind of things that we're doing now. We still need to do that. We still don't have a vaccine for this thing. Until we have a vaccine, yet we need to be vigilant. We really, really do. So be careful. Please be careful. That's why we're doing all of this virtual classroom kind of things even now, so that we could actually stay healthy. So please do that. All righty. Now let's talk about these growth models. We're going to start with 3 of them. First of all, we want to see if we have a constant 100 cases per day. And we'll say that there are only 100 cases on any given day. Then we're going to do a linear model that says 100 cases per day. So that means 100 more are added each day until we're done. And then we're going to talk about exponential growth. We're going to start with 2 cases and we're going to double each day, and we're going to see how that looks. So now you're going to have some hands-on work. Let's deal with this. So the constant model is always going to stay 100. And we want you to do this for, you can do it for 15, or you could stop at 12 really. And this will just have 100 cases in it all the way down because it is a constant model. Constant models are constant. So this is going to be 100 all the way through. All right, this is going to be the linear model. We're going to have 100x. So on the first day, we start with 100 people, 200, 300, and you see where this is going. And so then we want to do the exponential model. And this is going to be different because this is something you probably have never seen before. Some of you haven't seen this before because your math didn't go up that high, but this is just one little step. So we're going to do 2 to the first power is 2. 2 to the second power is 2 times 2, which is 4. 2 to the third power, if I can write this in here. 2 to the, I can do it. 2 to the third power, I can get my thingy right. Yes, it's going to be 2 times 2 times 2, and that's going to equal 8. 2 times 2 times 2 times 2, and that's going to be equal to 8. 2 to the fourth power. Oh, I'm getting better with this pen already. Oh, I spoke too soon. 2 to the fourth power is going to equal 2 times 2 times 2 times 2. And that's going to be equal to 16. And it goes on. Notice that it doubles each time. This is 2, 4, 8, 16. So the next number is going to be 32, 64, and all the way down. Then we're going to, just to say, if we had a 20% infection, those that were infected, if 20% of them had to go to the hospital, we're going to say that we want 20% of 2 and 20% of 4, 20% of 8, and then we're going to do 20% of times 16. 20 times 16, that's going to be 3.2, I do believe. Good, 3.2. And we'll continue this on down. These things also double as well. Notice that. Just like in your paper exercise that you did, these things double as well. So that's 0.4, 0.8, 0.16, 16, 3.2. So the next one is going to be 6.4, and it'll go all the way down like that. I want you to complete this table for me. And then I want you to pause this. Let me see. I want you to pause this, and we will be right back. All righty. We are back, and what we want to do is we want to go ahead and graph this particular model. My studying this with my tablet. We're going to try to do this anyway. We really are going to try to do this. Let me see. Let me see. Yes, 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 yes. So what I want you to do is to take the numbers that you got from this, and we want to go ahead and graph just like you did in that paper folding exercise that we did before. We're going to graph the constant model, the linear model, and the exponential model. We want to graph those kind of things here. And so we want to start out with an axis. Oh no, it's writing all over the thing. I'm going to start out with an axis, the y-x-axis, and forgive my writing. It's terrible. Hopefully you all will do much, much better at this than I'm doing right now. With this, should have just used the graph paper itself. And then we're at day, this might be day, we have, this might be day 5, 10, 15, 20, 25. I don't know why it's acting like that. Forgive me. 25, 30, 35, 40. We could say 5, 5, 10, 15, 20, 25, 30. Oh, it's messing all up. So this could be 100, 200, 300, 400, 100, 200, 300, 400. You get the idea. And then what you're going to do is take your data and say, let's say that a straight line is constant. Constant curve. So at 100, all of them hit 100, so you make a constant curve. And then let's do a dash, dot. Well, just do a dashes. We'll do that for our linear curve. And so you would start at 100. And you would make a line. And that would be for our linear curve. And then maybe you want to do dots for your exponential curve. And you would start way down here, almost at 0 for 2. And then you would actually make your dots where these things would go. Make your graph, do all that kind of stuff, and then we'll be right back. So go right on ahead. Go ahead and pause that video. We'll be right back. All righty. Hopefully your graph was better than mine because I was all over the place. Um, oh goodness, to make your exponential growth curve. But notice how the exponential growth is way higher, way faster than linear growth. Linear growth and constant growth start faster, but they know in no way, shape, or form keep up with an exponential curve over time. And that's why this growth is explosive growth. It's just like in the thing that you saw about the paper. You can go from the moon and from the Earth to the moon with I think it was 45 folds, and then on the very 46th fold, it doubles. So you go back to the Earth, the very next fold. So as I said, exponential growth is like crazy, crazy growth. And that's why we had to stop everything. Everything had to come to a screeching halt in the United States. If it hadn't, things would have gotten terrible really, really quick. All right, let's do this. In West Virginia, we have a total of 5,509 hospital beds that can take COVID patients. That's all we got. On what day, using the exponential model, would all these beds be full if only 20% of the COVID patients were hospitalized? And I want you to show your work. I'm going to stop this right now, and I will meet you right back on the other side. Pause and try to work this out. Remember, use that exponential model. All right, then. Take care of yourself. All right, you are back, and I am too. All right, let me see. So here's the thing. It says on what day, using the exponential model, would all these beds be full if only 20% of the COVID patients were hospitalized? Then you got to show your work. So this is a kind of thing that you got to, you could, this is going to be an interesting problem. Okay, so because we have, oh, I need my pencil again. Gotta find my pencil. Where did it go? Have you ever had a pencil and you just had it and it goes somewhere and you don't know where it went? I mean, I'm right. Oh, there it is. I got it. All right. So we got this. So we know that our exponential function is 2 to the x. That's right. And we have this. We don't know what x is, though. We have 2 to the x. And then we have to multiply it by 0.2. That's 20%. So we have 0.2 times 2 to the x is going to equal somewhere in the neighborhood of 5,509. So that's our equation. We gotta work this out. All right. So the first thing we do in working out this equation is we take our original equation and we simply divide both sides by 0.2. Well, I think I'm getting the hang of this now. So we got 2 to the x is going to equal, and I got to use my calculator to do that. I can't do that by hand. I have a TI Inspire. I would suggest that you get that calculator. That calculator makes everything groovy. A TI Inspire. You'll be able to use that for all your coursework, and you'll be able to use it for the upcoming SAT testing and all that, and ACT test that you can use it for. It's a beautiful thing. All right, so if I divide 5,509 509 by 0.2, I will get 27,545. Hopefully you got that too. And now what we got to do is find out which day, because this is X, which day am I going to get this with this particular number. So I'm going to have 27,545 people that, these are the people that are going to be in the hospital. No, these are the people that are going to be infected. 20% of those people is 5,509. On what day would we fill up all the hospital beds? This is what we're trying to figure out right now. So there are many ways to do this particular thing. One way is to simply double 2. You would, and then find out what number is close to this. You could do 2 to the first power. 2 to the first power is equal to 2. And then you can do 2 to the second power, and that's equal to 4. 2 to the third power, that's going to be equal to 8. And you can do this, double these, and find out what number goes here. Or, let me see, you can find out what number goes there. That's one way to do it. And because if you don't know natural logs and all that kind of stuff, this probably is the best way to do it. So let's guess. I'm going to guess, let me see. I'm going to say 2 to the 10th power. Find out what 2 to the 10th power is. I'll enter it. Okay, so I know that 2 to the 10th power is equal to 1,024. So that's too low. So let's go higher. 2 to the, let me go 2 to the 12th power. Oh no, that's really low. Let's go 2 to the 20th power. Okay. Oh, 2 to the 20th power is way too big. That's getting into the millions. We're not in the millions yet. Let me see. So let's go 2 to the 15th power. 2 to the 15th power. Ooh, okay. So we're getting there. So, okay. 2 to the 15th power is still too high. 2 to the 15th power is equal to, what is it equal to? What is it equal to? It's equal to 32,768. So that's too high. So let's go 2 to the 14th power. 2 to the 14th power. 2 to the 14th power is 16,384. So this X is going to be between day 14 and day 15. Between day 14 and day 15, you're going to have it'll only take 14 days if this virus was unimpeded for every hospital bed in West Virginia. Every hospital bed. This is every hospital bed. This is not ICU hospital beds. It's every hospital bed. So you're starting to understand why we really did have to close down everything. Because if we didn't, we would have been totally overwhelmed by the COVID virus. Everybody get that? All right. Let me see. So summary. COVID-19 is much more dangerous than the flu. It's not even playing. It's 10 times more likely to kill you, and it's a whole lot more contagious. The COVID-19 infection growth pattern is indeed an exponential one. And the reason why we had to shut down is because the potential of the growth of this virus, it will shut down everything. And that's why the United States had to close down not all non-essential activities. That's why it was kind of barren for a while. We're starting to pick up because we don't have as many cases as we used to. But I need you to stay vigilant out there, folks. I need you to protect your loved ones and everybody else around you. Keep wearing those masks. Keep on washing those hands. Keep on doing those things that you know how to do. And if you haven't started doing them, start doing them now. Start to do this. All righty. So what steps have you taken to prevent its spread? What kind of steps have you taken to prevent its spread? If you wish, you can, if you want to answer this and you want me to get those answers, I am found at david.cartwright@marshall.edu. That is me, and you can find me there. If you want to actually answer this question in text me form, we can chat over email. We can chat over email. All right, I've enjoyed doing this, and we are getting ready to get out of here and have some fun for the rest of this day. You take care of yourself. All right. Goodbye for now. I got another 2 more lessons for you. Go ahead and view those as well. All right.